In this lesson, we will make a practical design using the op-amp configuration we learned in the previous lesson. But first, we will take a small detour to learn about digital signal processing systems and their relation to analog electronics. Nowadays, in modern electronic devices such as cell phones and computers, most of the processing tasks are performed by algorithms rather than actual electronics. For example, when listening to audio, which is by nature an analog signal, tasks like filtering and equalization are performed digitally. This method of performing computations with signals using computers is called digital signal processing. A common digital signal processing system, which is called DSP for short, consists of the main following components. We have an analog or continuous signal coming from a sensor, for example. In the case of audio, the sensor can be a microphone. That analog signal is converted to the digital world where it is represented as a stream of numbers that constantly flows. The data is taken by the computer where some kind of algorithm is executed. The processor produces as output a new stream of numbers that needs to be converted back to analog using a digital to analog converter. DSP systems have advantages. One of those is that using a DSP system can result in a reduction of the number of components used in the overall system. One processor can perform thousands or millions of computations like sums, additions, multiplications. In a fully analog system, we will require many op-amps. The second advantage is that the algorithms have practically no variability compared to analog electronics. If we use a resistor of 1 kilo ohm, the actual value will not be exactly 1 kilo ohm. The components can have a variability that can go from a small percentage like 0.01% to even as high as 5%, depending on the cost we are willing to pay for the component. This variability in the components makes each circuit we build slightly different from each other. Another important advantage of a DSP system is that it is easy to modify and update. Since the main algorithm runs on a processor, changing the algorithm is as easy as uploading new code. Changing an analog system requires us to swap components and even in some cases, changing the integrated circuits and their connections. If DSP systems are so good, why are we learning the old analog electronics? Well, the DSP systems also have their limitations. First, the performance of a DSP system is constrained by the speed of the processor. A modest DSP system can process signals up to a few kilohertz. Analog systems, on the other hand, are extremely fast. Some specialized op-amps can perform operations on signals in the range of megahertz or even gigahertz. Additionally, DSP systems have a delay. They take some time to process the signal, while in an analog system, the solution is ready in a very short time. DSP systems also may end up consuming more power than their analog counterparts. A moderately powerful DSP processor can consume hundreds of milliamperes, compared to an op-amp which can consume a few milliamperes. Last, if you require performing few operations on voltages, using analog components can be much simpler than adding the complexity of a DSP system. On my day-to-day, I design boards that are a combination of analog and digital signal processing. Here we're going to see a common operation that I need to perform in order to adapt the analog signals so they can be processed by the digital part. In the diagram, you can see an overview of the system. In the synthesizer circuits that I made, it is common to have voltages that go typically from -5 to 5 volts. The analog to digital converters cannot take these relatively high voltages. It needs a signal that goes from 0 to 3.3 volts. Any signal outside that range is clipped. Similarly, after the signal is processed digitally, the digital to analog converter produces a signal that goes from 0 to 3.3 volts. It is necessary to adapt this signal back to the -5 to 5 volts range. In order to adapt these voltages, we need to use analog components, and with the knowledge that we have, we can create these operations. We have at least two options to implement the circuit. The first one is the following operation. We take the input voltage and we add 5 volts. This will make the signal go from 0 to 10 volts. Then we divide it by approximately 3 to get it in the range of 0 to 3.3 volts. The second alternative is to first scale the input signal and then add in an offset of 1.65 volts. If we try to implement this operation, you may find that we need at least two op-amps. The main issue is that the adders and amplifiers with op-amps invert the signal. For example, in the first case, when we add plus 5 volts to the signal, we obtain minus the input voltage plus 5 volts. The second stage multiplies by 1/3 and also inverts the signal back. Similarly, the second case, the first scaling inverts the signal. Then, when adding the offset, we actually need a negative 1.65 volts, which after it is added, the signs are fixed. Is there any way in which we can perform this operation using a single op-amp? Yes, but we need to do some simple processing on the digital side. In the previous implementations, a voltage of minus 5 volts corresponds to 0 volts, while a voltage of plus 5 volts becomes 3.3 volts. When the input is at its maximum, the output is also at its maximum. But what if we change the polarity of the signal? That way, when the input is at the maximum, the output is at the minimum, like this. Will that be a problem for the DSP system? Once the signal is converted, we get a number as output. For example, the numbers can go from 0 to 1024. On the digital side, it is very easy to restore the polarity by performing a subtraction. If we do 1024 minus the actual value, that way when we get a 0, we know that it's in reality a 1024 and vice versa. This operation is very cheap on the DSP side. If we do this trick, the formula to implement on the analog side looks like this. And in order to implement it, we need an inverting adder. However, there is a voltage of constant minus 5 volts that we need to provide somehow. In most of my designs, I use voltage references. A voltage reference is a special component that is used to provide a constant voltage with a good precision. Basically, you connect it to the power supply and it gives you the reference voltage out. The main disadvantage with voltage references is that they provide very little current, but if we use them only at the input of op-amps, that is not a problem since the current consumed is minimal. In this design, I added a voltage reference of minus 10 volts. I can use that reference for the other analog calculations if I need them. Here you can see the formula for the inverting adder. I have replaced one of the voltages by the voltage of the reference, which in this case is minus 10 volts. And now let's calculate the resistor values. Let's start by writing down the equation that needs to be satisfied for the minimum input voltage. When the input is minus 5 volts, the output will be 3.3 volts. Remember that for the minimum input, we produce the maximum output. The second equation is for the maximum input. In this case, an input of 5 volts will produce an output of 0 volts. With this, we have two equations and we have three unknowns, resistor RF, R1, and R2. We need to pick at least one value for the resistors in order to simplify the problem. In this case, I have picked the value of RF to be 10 kilo ohms. With that, we can use the function nsolve to obtain the values for the resistors R1 and R2. If you look at the results, you can see that they are 30.3 kilo ohms and 60.6 kilo ohms. I'm not actually sure if we can find commercial resistors with those values. Let's check which values are available and see if we can use them. Here you can see a table with the base numbers of commercial resistors with a tolerance of 5%. The way we use this table is by picking one base number, for example 1.2. We can multiply this number by different powers of 10 in order to get the commercial values. For example, we can get a 1.2 ohm resistor, 12 ohm, 120, and continuing up to 1.2 mega ohms. In our case, we need a 30.3 kilo ohms resistor. The closest we can get is 30 kilo ohm. There is no 60 kilo ohm resistor. The closest would be 62 kilo ohms. We can get closer by using two resistors in series. For example, a resistor of 56 kilo ohms in series with 4.7 kilo ohms gives us 60.7. We can pick different values for RF in order to find a value that is closer to the target. The process of selecting the best component value can be a bit complicated depending on the circuit, but for this formula it's still possible to find them after a few iterations. After a few iterations, I have found that the following values solve the equations exactly. A resistor RF of 3.3 kilo ohms, a resistor R1 equals to 10 kilo ohms, and R2 equals to 20 kilo ohms. Even when the solution is exact, we need to take into consideration that resistors have a variability. Each circuit that we build will behave slightly different. If we use resistors of 5%, we may end up with a few circuits behaving very far from the target values. In this plot, we can see like an aggregate of the results using resistors that have a variability of 5%. We can see that in some cases, the output can go as high as 3.4 volts or as low as 3.1 volts. One way of reducing the problem will be to use resistors of 1%, which nowadays they are very cheap. In the second plot, you can see the difference of using only 1% resistors. Another way of reducing the impact of the variability is to add a calibration step on the DSP side. For example, we can provide a constant 5 volts. On the DSP side, we can save the corresponding value in the memory. And we repeat the process for other voltages like 4 volts, 3 volts, and then we can use a table to get the actual values after calibration. Let's explore a second alternative for this circuit. If we use a positive voltage reference of 10 volts instead, we can use the subtracting configuration. In the first equation, you can see the formula for the circuit, and below, we can see the numeric formula that we are trying to achieve. Let's use the same values of RF and R1 from the previous example, since we know that these give us the exact scaling for the input. So RF 3.3 kilo ohms and R1 10 kilo ohms. With those values, the formula simplifies to the following. Now we need to design a voltage divider in order to obtain 1.65 volts of offset. The equation that we need to satisfy is the following. And after a few iterations, I found that the closest values for the resistors are the following. Resistor 3 of 5.1 kilo ohms and resistor 2 of 36 kilo ohms. In this lesson, we saw a practical application for an op-amp circuit that is used to adapt an analog voltage to a range acceptable by an analog to digital converter. We designed two circuits using commercial resistor values. We learned the process that can be followed to select resistors from a table of commercial resistors with a 5% of tolerance. We also created plots that display the effects of the variability in this type of circuits. In the next lesson, we will learn more considerations that need to be taken when creating circuits with real operational amplifiers.